Okay, let's get started. We're gonna be solving the weekly contest of LeetCode. I shared the link. Let's start with question 1. Sum of squares of special elements. So we are given a one-indexed integer array of length n, and we're told that an element at position I is special if it divides n, the size of the array, and we're asked to return the sum of the squares of all special elements of nums. We're even given the definition, the way to code this. So this is a very straightforward problem. The size of the array is up to 50 elements. So we can just go over all the indices, checking the condition, and then adding, hey, NCC, how's it going? And adding the squares of the values to satisfy the condition. So that is pretty straightforward. Let's code that quickly. So we want them to satisfy, well, let's define n here to make this prettier. Q4 was actually so easy looking back. I overcomplicated. Yes, I completely agree. I had a bug and it took me a while to finish, to get it right. And that's why I didn't rank as high as I expected. I finished the first 3 problems pretty quickly. So here we have to be careful that this is 1 based. So our I is 0 based, so we have to add 1. Otherwise we would have a division by 0. And here we want the square of this element. So this should solve it. So 21 and 63, which is the examples. Are there any edge cases? I don't think so. Even if there's one element, there's nothing special to it. So let's submit, and we get accepted. Okay, so pretty straightforward. Let's, as a follow-up, let's think about how we could make this faster. So we have to notice that we only care about the positions of the array that are divisors of n. Okay, so maybe we can find all the divisors of n and only go over those positions. How would we do that? So what does it mean for a number to be a divisor? So let's say that I'm having trouble with my tablet. I think. Okay, let's see if I can. I have to calibrate it, but let's try to do it anyways. So let's say that A divides n. So that means that there is an element a positive integer b such that n is the product of a and b. So that means that divisors come in pairs. For any divisor a, there's exactly one b that also divides n. So how can we go over all these pairs? So let's say that a is less than or equal to b without loss of generality. And notice that a cannot be greater than the square root of n, because otherwise the product of a and b would be greater than n, which is a contradiction. And yes, I think it's good to think about the proofs. So that means that we need to search for a in the range 1 and the square root of n. And notice that there is one special case when a is exactly the square root, when n is squared, then a and b are the same element, and we don't want to count that divisor twice, so we have to be careful with that. So let's code it for fun. Let's write a function that gets the divisors of a number. So we said that we were going to start from 1, and we want to stop before the square root, because the square root is a special case. Remember, don't use the square root function. You can write it this way, which is simpler. It doesn't use floating point numbers, and it's faster. So if d divides n, then we add v and also n divided by d. And here we need to see if d times d equals n, in which case we add d as well. Okay, so that's going to give us all the divisors of n. So now we can rewrite this as for all the divisors of n. Let's make sure that we make it 0 indexed, and that should be it. Oh, you can hear that? Yeah, I'm gonna close it for now. Okay, it passes the examples and accepted. So yes, this is faster. I mean, it's not that it matters for this problem, because in context, in general in LeetCode, you want to write the simplest solution to a problem if it's good enough. So it's good to know what is good enough. So this is just a lesson to understand how to go over the divisors, and to understand that we only need to go to consider a square root. So that's all for that problem. Let's go to question B. So we're given an array and a non-negative integer k. So this means that it can be 0. You choose an index I that hasn't been chosen before from the range and replace nums of I with any integer from the range, from nums of I minus k and nums of I plus k, both inclusive. And we want to count the number of equal elements in the subsequence. Return the maximum possible beauty of the array nums after applying the operation any number of times. Know that you can apply the operation to each index only once. So, and we have up to 10 to the 5 elements. So, so the first observation for these kind of problems is that the original order doesn't matter, because we care about a subset of elements that are equal, and we can apply the operation to any element. So that's usually important to notice, that the order is completely irrelevant, because maybe we can change it in a way that is useful to solve the problem. A second observation is that if two numbers are within 2k of each other, we can make them equal. We can consider the middle point of the two elements, and we can subtract up to k from the largest element and add up to k from the smallest element, and they both are going to reach the midpoint. And if they are farther away from 2k distance, then we cannot make them equal. Hey, Steven. So that means that we need to find a subset of elements, the largest subset of elements that are within that range, 2k. So maybe we can sort them, because when we sort the array, all the elements within that range are going to be a sub-array. And then we can do a typical two-pointer technique to find the largest ranges for every ending position. I noticed that sometimes this technique is called the sliding window. I think sliding window, I use that term for fixed window. I think windows have a fixed size. I don't know about you, but I'm very non-intuitive for this problem. Yeah, I guess if you break it down this way and you think about sorting them and you realize about this condition that you want to find a subarray that is that satisfies this condition, I think it is intuitive. I solved this one quickly because I've been doing some two-pointer problems lately. I think it took me just like 2 minutes. Yeah, I haven't thought about the line sweep solution. So let's do this one. So like I said, we want to sort them, and then we just apply the usual two-pointer solution. So we have 2 pointers, the left and the right pointers. These pointers defined subarray. And at each iteration of the main loop, we want to know the longest subarray that ends at right and satisfy the condition. That satisfies the condition. So that means, and we can assume that we already have the subarray that satisfies this condition for the previous element, for right -1. And therefore that means that the left pointer can only move to the right. It cannot move to the left. So that is the condition that allows us to do this 2-pointer solution. So while nums right nums left is greater than 2k, we want to increase the left pointer. So this is the range of the subarray because it is sorted. So at this point we have the longest subarray that ends in right. So we want to maximize that, and the size of the subarray is this because the pointers are inclusive. So this should solve the problem. We get 3 and 4, which are right. Is there another edge case? I don't think so. Accepted. By the way, do you hear any noise? Because in the previous streams, when I watched the bot, there was a noise, and I'm trying to improve the sound. So let me know. Okay, we're halfway there. Minimum index of a valid split. So we are given the definition of a dominant element, which is an element which has frequency greater than half. And we're even reminded that there could only be at most one dominant element in an array. That's very kind of them. So we're asked to do a split into 2, a prefix and a suffix. And none of them can be empty. So this is a partition, and we want the both sides to have the same dominant element. Denotes the subarray ending and both ending inclusive. Denotes minimum. If no valid split exists, return -1. So this is a kind of an odd problem, I think, because you can solve it by just applying a technique without even making some basic observations. So let's first do it the brute way, in a sense. So we can go from left to right, and we want to quickly know the dominant element of the left side. And if we know what the element might be, then we can check if it's also the dominant element of the right side. And a simple observation is that the only candidates to be the dominant element are the most frequent elements, any of the most frequent elements. If it is not a most frequent element, then it can be the dominant. So we only need to keep track of a most frequent element to the left side, and that's going to be it. So let's a most frequent element. Let's initialize it with some value that doesn't matter. And we're also going to have the count of all the elements and also the count of the prefix. So we're going to try with all the possible i's. So this cannot be the whole array, that's why we go up to n-2 inclusive. And now the only element that could exceed the most frequent is the current element, the element in the ith position. So if the count, so we count it, and if the count of the current element is greater than the count in the prefix of a most frequent element, then we change it. Okay, so now we have our candidate to be a dominant element. So what is the condition? The condition is that the count of a most frequent element times 2 is greater than the size of the prefix, which is I plus 1, right? Because if we are at 0, there's one element. So if that condition is satisfied, then this is a dominant element of the left side. And now we just check if it is a dominant element of the right side. And that is going to be the total frequency minus the frequency of the prefix So that is the how many times it occurs in the right side and again we multiply this by 2 and we check that it's greater than the size, and the size is going to be the total size minus the size of the left side, that was 1i plus 1, and if we found it we just return it, and otherwise we return -1. So that should solve this. 2, 4, and -1 looks good. And accepted. Cool. But now we can make an observation, another observation, which is that if an element is dominant on the left side and on the right side, then it must be dominant on the entire array, right? Because it appears more than half on one side, more than half on the other, so it will appear more than half in total. So that means that the only candidate to be a solution has to be the dominant element, if there is one, of the total array. So let's find that, and then we don't need to count them all, we just need to count how many occurrences of the dominant number. So it's the same solution, but we can avoid having these counters. I mean, it's the same thing, but let's do it. So the dominant is going to be, we check an element with maximum frequency. So out of the count, we want to take into account the so out of the keys, we want to take into account their count. We get a maximum. And now, if it is not dominant, I mean, the fact that it's one of the most frequent doesn't mean that it's dominant. If it is not dominant, then there's not going to be a solution. So if it is not greater, then we return -1. So a most frequent number, we don't need this anymore because we know it's the dominant. And here we don't need a counter, we just count the occurrences of the dominant element. And here we want to check if num_psi is the dominant element, and in that case we count it. We don't need this, and pretty much delete. So here we want the count of the dominant minus the count of the frequency, and that should also work. It's a little simpler. Okay, there's a bug. Let's see, are we finding the dominant correctly? Oh, so we are returning here. Oh, this is the count. Yeah, this is silly. The count of the dominant. Okay. We're not committing the same mistake. No. Okay. 2, 4, minus 1. Accepted. Cool. I see how you could solve this without using any data structures. What do you mean? I mean, I'm just using this counter. Okay. So let's move on to the last question. Length of the longest valid substring. You're given a word and an array of strings forbidden. A string can be valid if none of its substrings are present in forbidden. Return the length of the longest valid substring of the string word. Okay, and this is the usual definition of substring. The word is up to 10 to the 5 characters long, and we can have up to 10 to the 5 forbidden strings, but here's a very important part here, that the forbidden strings can be up to 10, size 10. So always pay attention when there's some small numbers in the constraints. Those are usually important. So yes, the idea here is to let's say that we want to find the longest substring that starts at the ith position and satisfy the condition that it doesn't have any of the forbidden words as a substring. So let's say that we could find the first position in which, starting from I, we get a match to one of the forbidden words. Okay, so let's say that here we find a match. So so let's say this is the word bad. So that means that we cannot consider this whole substring, but maybe we can count right up to the character, the position before J. So that's interesting, but what if there is another match that starts after I but ends before J? So we could have something inside here, and that will mean that we also have to stop before the end of this other substring that starts in a position after I. So that means that the longest substring that is an answer starting from I we have to consider all the ends of these matches that start in positions from I to the end of the string. Notice, by the way, if there could not be a match starting from I, for example, or any of these positions, and in that case the first element that we cannot match is the nth, because it's outside the string. So we can consider that j is equal to n in that case, and we don't have to have special cases. So how can we find the minimum end of all the substrings that start from I to the right? We can go from right to left, calculating this for every position and keeping track of the minimum end, and that is going to give us the end that we want. So let's start coding that. So we said that we wanted to go from right to left. We're gonna keep track of the longest substring, and we also want to keep track of the smallest end of the matches that we found. Initially it is n, and when we are considering the substrings that start at I, let's say that we have a function to update our j with the minimum between j and a match from a match of word from position I. Okay, so that's going to give us the j that we want, and that is going to give us the answer. Okay, so now we can focus on implementing this, and a good way to a quick way to do that is to use a try data structure tree. So we can match with all the forbidden words at the same time. So I'm not going to go into the details of the try data structure. There's a lot of introductions. I just wanted to show this example. I think one important idea to notice is that the nodes represent prefixes. So sometimes it gets confused, and the letters, notice that the letters are in the edges, and the nodes have prefixes. So in this example, seems like they are counting the frequencies, but in our case we only need to know whether a prefix is a word in the forbidden set. So even though this might seem complicated if you haven't seen it before, but the implementation is pretty simple. So we want to create a node of the try. I guess we can call it try node if you prefer. And we are going to have our edges And we're just going to use a dictionary for that. I'm thinking that maybe we can even use a default dict for this. I haven't thought about this before, but I think this makes sense. And then we want to know if the node is terminal, in the sense that it represents a word in the set. And initially we're going to say that it is not, and then we are going to change it. So let's say that we want to add a string to the try. So we go over the characters in S, and we want to check the next node for this character. And I think this is it for this. So finally, when we reach the end, we want to mark this as a terminal node. Okay. So let's call this like this, and we create the root node. And we added forbidden, I don't know how to type, forbidden try, and the word. So okay, so now we have a try with all the forbidden words, and we want to implement the match, which is also going to receive the root of the try. And we want to go over all the elements from I to the end of S. And like we said, if we don't find a match, we're going to return the length, which you can think about the first element that we cannot match, that we cannot consider in our string. So here we want to know, so we want to consider the shade character, and we want to know if so if it is not there, that means that we won't find the match. Otherwise, we advance our node to the next, and we want to check if it is terminal. If it is terminal, we want to return this. And I think that is pretty much it. So we get 4 and 4, which are the solution. And accept it. All right. So I hope that was clear. I think the implementation is pretty simple and it's pretty efficient. Match. Can you explain match? So the interface of match is like I explained here. We want to find the longest substring that starts at I before we find a match to any forbidden word. So it is going to return the position J, where J is the first character that we cannot include in the substring that starts at I. So in order to do that, we start going over the try data structure, starting from the I position, and we start going down the try, consuming the characters. If at any point we didn't find, we don't have a next, that means that prefix is not it's not a prefix of any words in the forbidden set. So in that case, we finish, and the first element that we cannot match is the total length. Otherwise, we move on to the next node, and if it is terminal, it means that we have found a match. This is the first match. Notice that we only care about the first match, because this is the one that is going to limit our substring. And when we find a terminal node, we found a match, and we return that position. So yeah, I think this is as simple as you can do it. I hope I had the clarity of thought that I have now to implement this quickly during the contest, but it took me a while. And it wasn't as pretty as this solution. So notice that it's important that this condition that the forbidden words are at most length 10, it's important to make sure that match is quick, because match is going to have it's going to do at most 10 iterations. That's why this is fast. I think that we could, I think this is solvable for arbitrarily long substrings, but I think we would have to use Aho-Korasic, which it's a kind of try, but whenever you get a mismatch, you backtrack. It's kind of a KMP type of matching, but with a dictionary. So when you find a mismatch, you go to the longest suffix that can still match the dictionary. That is the idea. I mean, it is tricky to implement. I would not recommend to implement it during a contest. I did think about doing that during the contest, and I regretted not having that ready, but then it turned out that it didn't matter. So yes, I think those are all the questions. I try to explain them as clearly as I can. I think the explanations should be easy to follow. They don't require much previous knowledge, I think. So yes, that's it. The bot is gonna be up when I finish the stream, so you can watch it later. And I'm planning to do this for upcoming contests. So thanks for your support, and see you in the next one.